Hold on. Hello?
Hello?
All right. So, yeah, welcome everyone to the Game Development Club. All right. So I just started my recording. Welcome everyone to the Game Development Club. Today we are joined by Mathew Kirschbaum, who you all know in one form or another, I believe. He's done some stuff with Pyrebug, but he's a UConn senior studying CS, and he is going to be talking about the wonderful, incredible reality that is Git and how we can use that to travel through time. So I'm going to give the floor to Matt, and yeah, take it away.
Hey, great. Thanks, Josh. So I'm Mathew Kirschbaum. I know most of you know me either through Pyrebug or wherever else. I am not so much into the game dev side of things, but I've been working in software engineering for a few years, and one of the big overlaps between software engineering and game development is you have to share your work, and a tool that's used in both like normal software engineering and game development is Git. So that's what I'm going to be talking about today. So first, quick plan. I'm going to be going over a lot of different parts of Git. It's a pretty big system, but we're going to be going over mostly just what you need to know. So first we're going to go over the fundamentals of Git, how it works, the different building blocks of Git. Then we're going to talk about branches, remotes, and some other stuff. And then at the end, we're going to go over some of the best practices I've seen. And I know Git is a little bit tough and can be confusing at times. So I've got the general chat open on my phone, so if at any time you have any questions, just throw them in there and I'll be sure to get to them. So I guess starting off with the fundamentals, I guess why would you first of all want to use Git? So there are a few reasons. First off, it's for sharing code. That's one of the biggest use cases. It's a very structured way to share code, so you're not doing something like Google Drive where you don't have much of a history to your code and it's a little bit tough to share everything and it's a bit slow. Git is much more structured than that, and you can see the history of your code in the different versions, and it has a lot of different features. And as I mentioned, you can also go back in time with Git and see the different iterations of your code. So if you have something called the oh no second, that instant where you screwed something up really bad, Git helps out with that. So you can just go back, undo your changes, go back to an earlier working version of the code. So at the underlying level of Git, what it really does is track changes in your code. Let me get a laser pointer, right? So if you've got this version of a text file beforehand, roses are red, violets are blue, this line rhymes with blue, and you change it to this one, the only thing that changed is this last line. So that's really all Git cares about. It's not going to store these two lines twice because they didn't change in between. The only thing it changes is this difference, which is also called a diff. Which is basically the line that changed, what got removed, what got added. That's really all that Git cares about is the changes. So there's three parts to the Git ecosystem, kind of. There's the working directory, the index, and the repository. So these are where this is the sort of track that all of your changes go through in Git to be saved in the repository. So first off, you've got the working directory. That is what files are on your hard drive right now. If you're working in an IDE or a text editor, whenever you edit files, you're working in the working directory. And then the second of these is the index. People also call it the staging area. And this is how you tell Git what you want Git to remember. So if you changed, say, 3 different lines in a file, but you only want Git to keep track of the change made to, say, 2 of them, this is how you do it. So you add those 2 lines to the index, but you don't add the 3rd line. So that's where the changes are built, and you build this package of changes called a commit in the staging area. So a commit takes all of your changes that you make at once and packages them essentially into a little box. And that box contains a few things. It contains a message that you write that basically just describes what happened in this commit. So usually that's what bug did you fix, what feature did you add, what did you change, and you write that. And then obviously a commit also includes what changes you made to the code. That's really the most important thing you're tracking here. And then a few other little things. Every commit has a unique identifier called a hash, and you can use this hash to point to a commit. So if you have, say, 10 different commits, each of those commits are going to have its own unique identifier or hash. And one of the uses of this hash is each commit points backwards to where it came from. So it points to its parent. That way you can build up from the beginning to wherever you are in the code and just layer all of those changes on top of each other, if that makes sense. And then once you have a bunch of commits, you put them together into what's called a repository. And a repository is essentially the entire history of all the changes that have been made to your code. At a very simple level, it can just look like this. You have 3 commits, A, B, and C. So each commit points backwards in time. So C would be your most recent change, and then the parent of C is B, and the parent of B is A. So you can layer all these on top of each other and figure out what did the code look like here, what did the code look like here, what did the code look like here. So this is a very simple example of a repository. And then as you get into more complex or larger projects, you have branches and you have a lot of different commits, and it can look a lot more complicated like this, but we're going to get into that. So does that all make sense to everyone? If you have any questions, again, just throw them into the chat. But looking at it all together, this is really how working with Git essentially works. So you have the working directory, again, which is the current state of the files on your hard drive. You edit those to do whatever you want to do, whether it's fixing a bug or adding a feature. And then you tell Git what changes you want to record. And that's usually called adding or staging. And then Git knows, okay, these are the changes you made that you want to record. And then whatever you didn't add is either not tracked or saved for later. But either way, whatever changes you do add go into the index, which is, again, the set of changes that you've reported to Git. And then once you report all the changes you want for a single bug fix or feature or whatever, you package all those changes into a package called a commit. And then multiple commits will build upon each other to create a repository. So that all makes sense. I'm going to do a pretty quick demo of just how that workflow works before we go on to anything else. So I'm going to make a new repository. I'll call that master for now. Most of these you don't need to worry about. Right, so I just made a new repository here, and by default you have a single commit. Sometimes this is called a big bang commit or an initial commit. It's just to get the repository started. So now let's say I want to make some file. We'll make it simple right now, just a simple print hello world. And let's say this is the only feature I want to make right now. It's just printing out hello world. Okay, we'll see this file changed. Specifically, I made a new file, so I'll stage it. So right up here, these are the changes in your working directory. You stage it, and this is the index or the staging area. And then you can write the message for your commit. So we'll say print out hello world. Then you can commit the changes, and now you'll see you have a second commit, and this commit points backwards to initial commit. You might not be able to see that line because it's kind of small, but you've got two commits.
In Git crack, and you can actually hit Control Plus and zoom in.
Oh, yeah. Great. Okay. Yeah, so we've got the two commits, and then just to reiterate, let's say we want to just add another feature, say name equals. So we'll just get this person's name, and we'll just say hello to them. So now going back, you can see in your working directory what's changed. We got rid of this line that says print hello world, and we added two new lines, the ones that I just wrote. So we'll stage those changes. We'll write a commit message, ask user for their name, then we'll commit, and now you can see we have three commits. Fairly simple so far. So now, moving on from that demo, if that makes sense to everyone, we're going to talk about branches, which is where things can get a little bit complicated if you're not careful. So first, this will be a very quick intro to graphs, because I found that that helps a little bit with figuring out how branches work. So a graph essentially is a set of nodes and edges. So graphically, like all of these dots are called nodes, and then all the lines connecting them are called edges. In the context of Git, the nodes will be the commits, the edges will be those pointers pointing back in time to a commit's parent. So adding on to this, we're going to just add a few layers to what we define as a graph. So now we have a directed graph where each edge has a direction. So usually that's written out like an arrow. So you can see we're getting a little bit closer to what a Git repository looks like. And then finally, sometimes you can have in just a normal directed graph, you can have cycles. So you can see 3 points to 4, 4 points to 3. You have a cycle. That doesn't really work in Git unless you have a time machine. So we have this thing called an acyclic graph, which just means there's no cycles. So here you can see there are no cycles anywhere. And that's really all you need to know about graphs. Is directed graphs have arrows, directed acyclic graphs don't have cycles. So if we look at a repository, that's pretty much what it is a directed acyclic graph. So you have each commit points backwards in time to its parent, and there's no cycles. There's this branch, but you can see there's no way to create a cycle because this one points backwards, this branch also points backwards, so there's no cycle anywhere. So moving on, let's look a little bit at what branches actually are. So these are branches. So the default branch is usually called master. Some people are trying to change the name of master to main or trunk. Traditionally, it's still called master, so that's just what I go with. And then here we've got a branch called feature 2. So essentially, all that a branch is a name that points to a commit. That's all a branch is just a name pointing to a commit. And then we have these special branches called tags, which I'll get into on the next slide. But they essentially work the same way as branches. They're just a name here. We have v1.0 and v0.1. And these, just like branches, are just a name that point to a commit. And then there's a special sort of branch called head, which I'll also get into on the next slide. So all of these branches, tags, and head, these are commit references because they point to or reference a single commit. They're also called refs. So branches are mutable, which means they can be moved. So say if we added a new commit right here, you would end up moving master forward to that commit. So it's mutable, it can be moved, it can be changed. And then a branch is also named, as I said. The biggest difference between branches and tags are immutable. So again, going back here, this v1.0 tag, if you added a new commit here, then you cannot move this v1.0 tag anywhere, which is pretty useful in, say, specifying different versions, which is how they're being used here. Because if you have a v1.0, you don't want to add any more features on top of that and call that like the new v1.0. You'd want to create a separate tag for that. And then head is a little bit complicated. You don't need to worry about moving head around. Git does that for you. It's a special type of ref that points to where you are in the repository. So here, if you're on the master branch, head will point to master, which points to this commit. But then say you want to switch to the feature 2 branch, that's called checking out a branch. What Git will do is it'll take this head and it'll move it over here to point to feature 2. And an interesting thing about head is it doesn't point, well, it can point to a commit directly, but the way you want to use head is it should be pointing to a branch. So here you can see it's pointing to master, it's not pointing directly here. If the head ref is pointing directly to a commit, that's called the detached head state, and that's bad because weird things can happen when you start working with a detached head state. So best practice, always make sure you're checking out a branch, not a specific commit. So again, checking out branches, Git will move the head to the specified commit. And then if you have any pending changes in the index or the staging area, Git will probably not let you check out a new branch. You'll need to either discard whatever changes you have so far or make a commit before you switch to a new branch. And merging branches is where it gets a little bit complicated. So back here, you can see we had 2 branches. We had this top one and this middle one. And then whoever is working on this repo wanted to take the changes and merge them together. So what they made is called a merge commit, and it's a commit that has two parents. So its first parent will be up here, and this is its second parent. And essentially what it does is it takes all of these changes that are up here, combines them into a single commit, and puts it right there. So any changes you made on this top branch will essentially be copy pasted down onto the code in here. Does that make sense to everyone? Not seeing any questions. Yeah, so as I said, it'll find the most recent shared commit, which in this case is back here. Right. So this commit is pointed to by this branch, and it's also pointed to by this branch. So it'll find this shared commit, and it'll say, okay, these three changes are not down here. So we'll take these three, combine them together, and just paste them right onto the end. So go back here, start working on a new branch. So you can click branch, enter branch name. We'll say goodbye. Let's say we want to make a feature that says goodbye to the user instead of hello. So fairly simple change to make. Just change hello to goodbye. Now you can see we changed this line from hello to goodbye. We want to stage that change. And then we'll write the message, and we have this commit. Now, let's say we want to make a change on the master branch. We can check out master. Now we're on master instead of goodbye. And now let's say a feature we want to write is we'll factor out this into a new function. Right. So now so we're still on the master branch, and these are the changes we've made. We've added the say hello function, we've removed the print, and we've added a function call. Let's stage those changes, write a commit message, factor out print into say hello function. Great. So now you can see why they're called branches. It's because the repository is branching out. So we have goodbye pointing to this commit, master pointing to this commit. Say we want to now merge them together. Can now merge goodbye into master, and then we have merge conflicts, which I guess I'll cover now. So merge conflicts essentially happen because Git is dumb. It doesn't know what to do if a line is changed on two branches and you want to combine those changes together. So it offloads that decision to you. So you need to figure out how to combine those branches because Git doesn't know how to. So that's what you're doing here. You're resolving that conflict. So let's get back to the code and see what that looks like. Okay, so you have the current change, which in this case is master because we're on the master branch. And you can see it says head because head currently points to master. We have checked out master. That's where our current changes are. and then the incoming change is from the goodbye branch. So there are a few things we can do. We can just get rid of the incoming change and just ignore that goodbye name altogether. So essentially nothing's really changed there. We can accept just the incoming change. For example, here, say hello function isn't doing anything, we're just printing goodbye name. Or we can do something different. For example, we can accept both changes. So here we're going to be saying hello to them, and then immediately we're going to be saying goodbye. So again, Git is dumb. It doesn't really know which one you want to do, which is why it's offloading that decision to you. We'll say for now, we'll just accept both changes, and it will just say hello Matthew, goodbye Matthew immediately afterwards. So now that we've resolved that, we'll mark it resolved, and now Git will let us commit and merge. So that's really all that a merge conflict looks like, right? You have the two different branches. Git doesn't know how to combine them, so it asks you how to, and you can either accept changes from the incoming branch, you can accept your current changes that are on the current branch, or you can do something different. You can combine them. You can do whatever you want with that. Okay, still no questions. Good. All right, and then a fast forward merge is very simple. So let's say we want to merge the changes from branch 2 into master here. There are no changes in branch 2 that aren't already in master, right? Because it's a line, and branch 2 is just backwards in time. There's no sort of branching off here. So if you try to merge them, what Git will do is essentially called a fast forward merge, where it just moves the branch forward. It doesn't create a commit. It just changes what branch 2 points to. Because if you were to create a merge commit, it would just be empty. There's no changes to incorporate there. Well, thank you, Josh. I'll give a minute or two just in case anyone has any questions, or to digest all that information. I know it's a lot. All right, it looks like nobody has any questions. That's good. So moving on to part 3, we're going to talk about remotes and a few miscellaneous features that are in Git. So first off, let's talk about remotes. So a remote is a copy of your repository that is somewhere else. And this is one of the biggest benefits of Git besides the keeping track of your history. The second biggest part of Git is being able to share your code with it. Excuse me. So yeah, a remote is a copy of a repository that is somewhere else, and Git has the ability to share your changes to the repository in both directions, both from the changes on your remote copied over to your machine and vice versa. So the changes you've made on your machine copied over to the remote. by default, the first remote you add is usually called origin, and the way that Git communicates with a remote is through these things called remote tracking branches, right? So you have a branch on your local machine called master. That same master branch will, of course, be in the remote copy, but Git needs to know kind of where the remote branch is relative to your branch. So it keeps a reference to that. And that's called a remote tracking branch. And the way it's written out is the remote name slash the branch name. And that way you can keep track of where the master branch is on the remote versus where the master branch is on your own machine. So how do you actually communicate with these remotes? So the first thing you usually want to do is a clone, and that just takes a remote repository from, say, GitHub, which we'll talk about in a bit. It'll just take the repository and just download it to your machine. You only need to do that once. That's just to get all of the existing commits and changes and files copied over to your machine. Once you have your repository both on your local computer and at the remote, say in GitHub, you can push your local changes to a remote. So that is the command. It's called push. And what that'll do is it'll take all of the changes you've made. So it'll see where the remote branch is. It'll see where your branch is. It'll take all of it'll take the difference between those two and just copy them up to, say, GitHub. So that's how you take your changes and share them with everyone else, is with pushing. Meanwhile, if you want to take everybody else's changes from a remote and copy them into your machine, the way you do that is with a fetch. So what that does is it'll update the remote tracking branches and copy in whatever new commits were added to that remote. But notably, it doesn't do anything to your local branches. It doesn't move them to update them. It just adds new commits and updates where the remote tracking branches are pointing to. If you want to update where your local branches are so then they're in sync with that remote tracking branch, you would need to do a merge, which is what pull does. Pull essentially is a fetch, so it updates the remote tracking branches, plus a merge, so it'll make sure that your local branch is in sync. And best practice, you want to push and pull pretty regularly, especially pulling, because if you don't pull and there are changes on the remote repository, Git won't let you push until you pull those changes down. So you want to make sure especially that you're pulling often, and then also you want to push often so then people are updated with your changes. A brief introduction to changing history. This is very often a thing you don't want to do in Git, but you do have the ability to. There are a few ways of changing history, most of which I don't even use. There's like squash, there's the reflog, a few things like that. The only real way that I personally ever change history is with Rebase. So Rebase takes an entire branch and just moves it on the remote. I don't have a graphic for this, so I can just draw it. So let's say we have let's say this is our repository right now. Master points to that commit. Branch 2 points to that commit. So essentially, what rebasing does is it just takes this entire portion and does that. It just takes the entire branch and has it point to somewhere else in the repository. So this is an example of changing history because you are changing what this commit points to. And generally, changing history is not a good idea in a shared repository, because once somebody else on the team tries to pull that change, the repository is going to be in a really weird state. Things are going to break usually. So rule of thumb, do not change history on remote branches. Local branches is generally fine if you know what you're doing, but again, don't do it on a shared branch. All right, so moving on to one of the most popular remotes, GitHub. I've often seen these two terms, Git and GitHub, used interchangeably. That is not correct. Git is the protocol. It's the system that lets you do all of these tracking changes and sharing code and all of that. GitHub is just a server that lets you store remote repos somewhere, right? They're completely different. And there's also a few alternatives to GitHub, which are not as popular. But for example, there's Bitbucket. Bitbucket is mostly used like in enterprise companies. GitLab is a newer one. And then, of course, you can self-host your own remotes. I don't think I've ever heard of anyone doing that, but it is something you can do if you want to. And then on top of the normal functionalities you have in Git, GitHub has a few extra things you can do. So the first one is called forking. So that's when you take somebody else's repository that you've been looking at and you want to make a change to it. You want to add a feature or something, you would fork their repository. And what that does is it copies their repository into your account on GitHub. And then you can make whatever changes you want to that. GitHub also has what's called a pull request. So say after you fork and you add a new change, you can submit a pull request to the original repository, which essentially says, hey, I've made this change. Can you merge it into your version? And then if the owner of the original repository approves, then GitHub will take the branch from your version of the repository. Licensing on GitHub. Okay. I don't know much about that, but I'll do my best. A pull request takes your branch from your version and merges it into the original repository. So forking and pull request, very related. And then finally, among many other features that GitHub has, another big one is issues, which allows you to open an issue for a feature change or a bug. And this essentially allows you to write up a description of whatever the bug is, or whatever feature you want to be added, or whatever change you want to be made. And then a bunch of users can discuss about what that feature change or bug fix might look like, or how to reproduce the bug. It's essentially a mini forum to discuss desired changes or bug fixes or whatnot. So these are all specific to GitHub. They're not specifically part of Git, the protocol. Okay, so yeah, I'm honestly not too sure how licensing on GitHub works, but if you want to at the end, Josh, you can talk a little bit about that. But moving on from remotes, we have a few last things to talk about with how Git works, a few extra commands. So reset is sort of like an emergency button in Git. If you screwed something up really bad on your working directory, or you just want to undo all of your changes that you've made, you can reset the state of the repository to a specific commit. There's 3 types of reset: hard, mixed, and soft. Usually you want to use hard reset. It'll revert the current branch, your working directory, and your index to whatever commit you specify. So that is essentially the nuclear option. It wipes out all of the changes you just made, which is definitely useful if you screwed something up. Mixed is the default way that reset works, and it'll keep the working directory how it was, but it'll clear out the index, and it'll move back the current branch. So this is if you want to clear out some commits that shouldn't have been made, but you want to keep the changes that have been made. Soft reset, I don't think I've ever used it. Essentially, the only thing that happens is it'll move back the current branch, but it'll keep the changes in the index and the working directory. But again, hard is the nuclear option. I think I use this the most. Mixed is if you want to undo some commits, but keep your changes. Then reverting commits, it's a way to undo changes without modifying history, right? So it'll essentially take, you can, actually I'll do it in Git Kraken. Say we want to like undo this change. I'm not sure how well this will work because there's a merge and stuff in there. Yeah, well, I'm not going to bother with that. Essentially, what it does is you take a single commit that you want to undo, and it'll just reverse all of the changes. So any lines that you've added, it'll remove. Any lines you've removed, it'll add back. And because you're creating a new commit to do this and adding it onto the end of your repository, it doesn't actually change the history. So if you want to undo something on a shared branch, this is the way to do it, is create a revert commit. I think this is the last feature that I'm going to go over for Git, is the .git ignore file. And the .git ignore file lists all of the different files and folders that you don't want to include in the repository. So if there's an untracked file, Git will first make sure that it isn't listed in the .git ignore file. If it is, you just can't add it to the repository. So this is a really useful feature for keeping your repository clean of a few things. Maybe the biggest thing that git ignore helps with is secret keys. I don't think it's that useful for game development, specifically the secret keys part, but if you're doing something like web development, Usually the web server will store some sort of secret key or encryption key in a file that it can reference. You never want to upload secret keys to a repository, because even if you delete that file, and like commit removing that file, you can still go backwards in the repository and see the contents of the file you removed. So again, don't commit secret keys to a repository, and the git ignore file makes sure that that doesn't happen. So you can just automatically ignore whatever file has a secret key in it, and Git just won't let you add it. Other uses, local configuration. So VS Code, it's not here, but Visual Studio Code, for example, adds a .vs Code folder to some files. Actually, if I try running the code, it might do it, or not. Anyways, Visual Studio Code adds a .vs Code folder that has some config for your workspace, what extensions are enabled, things like that. Visual Studio adds its own file or folder rather. Mac has the .dsstore folders or whatever. I think you want to keep those ignored.
I would say git ignore for everybody in the game dev field is extremely important because Unity itself has a lock file, and if you don't use the Unity git ignore and apply that when you're initializing the repository, you're going to have a lot of problems with committing anything without closing out your entire Unity client. So, yeah, that's the example that I'd have.
Yeah, local config and Unity files like that, and then finally build artifacts. So things like the executable that you build, any like object files that are involved in linking together an executable, anything like that doesn't really make sense to upload. Josh, does Unity automatically like set up a git ignore file?
No, but in the public git ignore repo that GitHub outputs, there's an official Unity git ignore.
Yeah.
So Matt's pulling it up now, and this is an official repository for nearly every single thing you could imagine. There's the Unity git ignore. And this is actually just GitHub puts this out, and they work with the actual developers of the engines and IDEs and softwares to make sure that these are properly kept up to date.
Yeah. So, you can write your own, but I found it's usually easy to just copy one straight off of here. Excuse me. So if you're using Visual Studio, this will just ignore every file in the .vs folder. I don't know if there's like there's not a .vs code, but you can like add that. And there's ones for like every language that matters. So like for Java, you'd ignore the compiled files and log files and like .jar. It's a very useful feature.
Totally.
So that's, I think, the end of the Git features I want to cover. There's a lot more. Git is a very large, very powerful system that has a lot of features that most people don't use. So like Squash will take a bunch of commits and combine them together. I think I mentioned that briefly when I talked about changing history. Submodules lets you like include other Git repositories in your own repository. Reflog, commit hooks, file checkout. Those are all pretty advanced topics. Cherry picking, you can take a single commit from another branch and just paste it onto your current branch. LFS I know is very useful with game development. I've never needed to use it, so I can't really speak about how that works. Bisect I found useful in a few cases. It lets you essentially jump around the repository in a very structured way to figure out specifically what commit resulted in, say, a bug or something not working. These are all really cool features, but they're definitely advanced, and you don't need to know them except for like maybe LFS, large file storage, if you're working with game development. So before moving on to that, Josh, if you want to talk quickly about licensing and if you have any input on how LFS works.
Yeah, I can talk about both. So GitHub licensing is pretty much up to you. You can set your license on GitHub. So if Matt goes to, I guess if you pop open any repository, let's see. I actually just forked. If you go to my profile, I just forked a repository from a backgrounds generator. It's called. Oh, it's up there. Triangleify. It's that one. This is made by a software engineer out of California. He's super cool. He has a website where you can pay for backgrounds to be made with his generator, or you can just make them yourself. And if you scroll up a little bit, there it is. Yeah, so it's a general. There's different types of licenses. He says that like this one's a general public license, so you can see there that GitHub actually has all these licenses built in, and you can set these licenses yourself. So his permissions are that you can use it for commercial use, you can modify it, you can distribute it, and all this stuff. He asks that you ask him before like doing that specifically, but it basically is just a rundown on what all these licenses do. Most people use the MIT license if they're not looking to like make money off of it. But for this guy specifically, he chose his license because he said that with his software, anything you make with his software, the open source software, you have the rights to. So essentially, it's like his example is like if you make something in Photoshop, it's as if you made this thing in Photoshop. That's the rights that you have to it. And yeah, Matt's going through the list now on GitHub as well. So you can say none. You can say that there's no license and no rights, which is fine. You don't have to worry about choosing a license, especially if you don't plan on putting this out publicly or you don't want to share it with too many people. Typically speaking, you won't be using this. However, if you make a larger game project or you make something that you're proud of and you want to share it with a lot of people, generally speaking, you should go with the MIT license. Or if you want to share it with everyone for free, the Creative Commons Zero license is typically the way to go. But yeah, that's generally how that works.
Yeah, the two that I know the most about is GPL3. And MIT. MIT is essentially do whatever you want with it.
Yeah.
GPL3 is very much along the same veins, except there's like a few clauses, mainly any changes you make to something licensed under GPL3 also have to be licensed under GPL3. And there's choosealicense.com has good explanations for all these.
Yeah, there's lots of resources that you can check out.
Yep. And then I guess if you want to say anything about LFS, because I've never really used it.
Yeah, so LFS it's just large file service, and basically, shortest answer for that is you have your Git client, which can interact with GitHub. GitHub has 100 megabyte file size limits. So if you try to commit anything on GitHub that's 100 megabytes or over, you'll have to actually delete that commit from your history and then figure out what you're going to do. So If you just don't commit files that are over 100 megabytes, you're fine. Or I guess if you don't stage them, you're fine. But what LFS is it's essentially a separate. It's almost a separate repository that has all of your large files of over 100 megabytes. And this can be stored. This has to be stored on a private computer or server. So when you push to your remotes, you're pushing every file that is over 100 megabytes to your large file storage, and you're pushing everything that is under 100 megabytes to your remote storage, or I guess your remote repository. It functions as sort of a this diagram is pretty good. It basically explains what I'm saying. So you have your large file storage and you have your regular storage. So yeah, so that's basically what it is. It's very tricky to set up and get just right. Remember that if you are modifying files of over 100 megabytes, you're going to have to store every modified version of those files if you really want to go back. Depending on how many you have, that can be insanely large. Some things to keep in mind as well. Amazon Web Hosting offers this service with like data packs, and you can actually spend a certain amount of money to transmit up and or down certain amounts of data to a large file service that they host for you. It's pretty strange. I'm not gonna lie, it's pretty like science fiction to hear I'm gonna go buy this data pack, and that's like, I think that's just really funny. But yeah, that's how it works. If you have terabytes of SSD storage, I'd recommend doing it yourself. But since most people don't, there are a few other options. One option for large file storage is to keep it local only, which can be kind of tricky, considering that if you're working on a team, that's hard to do. Another thing that I've seen some people jank together, I forgot the name of it, but there is literally a large file storage buffer that functions as LFS, but will upload and download things from Google Drive, because if you just have a lot of storage on Google Drive, which is a lot cheaper, that just works. And it's super weird and it's super jank, but I mean, it's cheap and it works, so people make it happen. But yeah, that's what LFS is. If you're in the DMD program, you have definitely used UConn's LFS storage, which actually is accessible via github.uconn.edu, or is it uconn.github.edu? I can never remember. Either one of those. They have directly on there, every repository comes with LFS support. And if you're working at a big organization, they will definitely have LFS support as well. So yeah, that's how it works. I hope the explanation wasn't too confusing. But yeah, that's pretty much what it is. Oh, and this is much like how Git and GitHub are separate. This is separate from both of those. This is a completely different system. So yeah, this is third party, which is super strange if you really think about it.
Yeah. So yeah, that's how LFS works. Thanks, Josh. I guess before we get into best practices again, if you have any questions, throw them in general. But otherwise, we can move on to best practices. All right, no one's typing. Okay, so best practices. So, yeah, we've gone over most of the fundamentals of Git and what you need to know to use it. But there are a lot of best practices that can help you out with making sure nothing goes wrong and to standardize workflows and a bunch of great stuff like that. So first off, there are a few best practices that apply to committing. So the first one, naming a commit or that message that you wrote. You want it to be descriptive but also concise, right? So in GitHub or in GitKraken, rather, you only have so much space to to see what the message is. And for example, right, yeah, there's only so much space on a terminal to print out the commit messages. So you want to make sure they're pretty short, but they also describe what happens. And sentence syntax, I'm not sure how well I really... Yeah. So a good practice that I found is saying this commit will say goodbye instead of hello. Can I zoom that in? Yeah. Right. So this is just a true statement. This commit will say goodbye instead of hello. Get rid of this commit will. That's your commit message. I found that's a pretty good standardization to make sure that everything is standardized and makes sense. It looks like I followed that here, which is good. One thing you really don't want to do is have a commit message like does stuff or fixes the thing, because that doesn't describe at all what you did. Even though I do recognize that doing that is very tempting with non-shared repositories. And then also the contents of a commit, the changes that you make, it should be a single cohesive unit of change. So it should be a single change, and then it should be self-contained, which means everything relevant to that small unit of change should be included in that commit. And it should be related, so you shouldn't have two different changes in a single commit. Those should be two different changes. And these best practices kind of help make sure that happens. So it should be a descriptive but concise message. If the message is too long, you're probably doing too much stuff in a single commit. The word and typically shouldn't appear in a commit, because that means you're doing multiple things at once, which is not a thing you should be doing in a single commit. Generally, a good rule of thumb is you should make sure that before committing, your code should at the very least compile. Depending on what you're doing with the commit, it may or may not necessarily need to work as intended, but it should definitely at least compile. And then, as I mentioned before, it should be self-contained. So if you're working on a change between two commits, say you forgot a semicolon somewhere, instead of, I can work on it here. Instead of creating two commits, you can amend a commit as long as you haven't pushed it yet. So say here I haven't even merged these yet. Okay, we'll go into the test repository. Okay, this is just some files I was testing out to make sure everything worked. Let's say say hello name number. Let's say you just let's say you want to say hello twice or whatever for some reason, and you stage the change. Say hello twice. Make the commit. So now you have this change in here. And then if you go in and you say, okay, python3./main.py, yeah, there's an error. Oh no, I forgot a close parenthesis. You add the close parenthesis. you can see that's all that changed. Now here, you don't want to create another commit that's like fix the closed paren. You don't want to do that because then that just looks dirty and it's not self-contained. What you can do instead is amend the commit, and it'll just combine whatever changes you just made into the previous commit. Again, this is changing history. Don't do this if you've pushed already, but it is very useful if you forgot something in a commit and you haven't pushed yet. You can just amend whatever changes you need. So that's very useful for making sure everything stays self-contained and related. Yeah. Remotes, some best practices. Again, never change pushed history. It just screws up a bunch of stuff. So don't rebase shared branches. Don't amend commits that you've pushed already. Don't squash commits that have been pushed. Things like that. You want to make sure you push at least at the end of the day. So then if the building catches fire or whatever, all of your changes are at least pushed up and saved. And then if you have a team member that wants to work like early in the day or whatever, they can just pull down your changes and have them instead of them sitting on your computer overnight. And then the last big rule of thumb with remotes, make sure you pull before working, so then you have everybody else's changes, and then you're not creating you don't have to create merge commits to update your remote tracking branches, because that can definitely get a little bit of a pain. So just make sure you pull before working, and then as an addendum to that, pull before you push as well. Again, branches makes things a little bit difficult. There's a lot of different philosophies for how to work with branches. Git flow is pretty popular. This is actually an example photo or picture from the Git flow website. I've never really used it that much. I feel like it's a little bit too complicated, but essentially the way Git flow works is you have this master branch, and the master branch is only for releases. You have a hotfix branch, which is if you need to make a bug fix really quick on a release, you do it there. Not sure what the difference between master and release branches are, because I've never really used Git flow. Develop is where you can copy in hotfixes to the development code. You can create feature branches off of develop and merge them back in. Again, I don't really know the specifics of how Git flow works. I've never really worked with it before. But no matter what workflow you're working with, you generally want to keep the master branch clean and always working. A workflow that I found while I was doing some interviews with companies is Mojo Tech, is a company I interviewed with. They have their Git workflow on a blog post, and I found this is actually a really well-structured way to organize your branches. So you'll have, again, the master branch, which you want to keep clean and always working. So if you want to make a feature, you'll create a feature branch off of master. You'll implement that feature on the branch, and you'll submit a pull request. So you'll go to your team leader, whatever, and say, hey, this is a feature branch. I want to merge it into master now that the feature is done and implemented. The team will review the code. It'll go through a test suite or whatever other verification you need, and then you'll merge the branch back into master. It's a fairly simple workflow, but it keeps things organized. And then just some things that they mentioned in the blog post. You want to first of all, make sure your feature branches are local. You should really be the only one working on a feature. If there's multiple people working on the feature, it's probably too big and can be split apart. Which means you can rebase your feature branch. So going back here, let's say some other feature has been added to master. Right? Someone just added a new feature onto the master branch. You want to make sure that your feature branch you're working on is updated with those changes. So you'll rebase onto master fairly often to make sure that you're always up to date, which of course means you don't want to push the feature branch until you're sure it's complete. Another thing, you can tag your commits. So this is not really like a feature of Git, but let's say updates the removes buffer overflow. Let's say that's your commit message. Just to help with readability, they suggest you can do something like this. Just throw like fix at the beginning if it's a bug fix, or like docs if you're updating documentation, things like that. Seems like a pretty nice way of organizing commits and keeping everything readable. And then finally, a good branch name policy, which I've seen in a few different workflows, is your initials / a short description of what that feature is. So for me, it would be MFK / random terrain generation. And I think that's pretty much it. We've got quite a bit of time left if anyone wants to ask any questions, clarify anything.
This is the part of the presentation where everybody unmutes their mics and claps. Yay! Yay! That was really nice.
Thank you.
Oh. That was really insightful. That was awesome. I loved it. That was really insightful. It was really great.
Thank you.
Absolutely fantastic. Fantastic presentation. I personally don't have any questions, but I will throw it to the floor. See if anybody does.
All right, I guess
Devin's
not.
Well, Devin is.
Oh,
Devin wasn't.
Devin
Yeah. It was thorough as heck.
Thank you.
It was extremely thorough, well thought out, well made.
Thank you.
And it was fun. I liked all the different stock photos. They were nice.
I love this stock photo so much. Actually, let me stop.
Yeah, I was about to ask.